Hi everybody, Mr. Neff here. Let's try some of those projectile motion problems from last night. 37 says an archer shoots an arrow horizontally at a target 15 meters away. The arrow is aimed directly at the center of the target, so if there was no gravity, the arrow would fly right out there and it would hit the target, right here. But there is gravity, so it actually comes down and it falls down to here, and that's 0.52 meters. That's 52 centimeters down. They say, how long does it take for the arrow to reach the target? So really it's how long does it take for the arrow to fall 0.52 meters, and that's the same as it takes anything to fall 0.52 meters. So if I'm doing this, I'm going to say that the initial velocity is 0. You might say, oh no, but it's shot horizontally. Well, I say exactly, it is shot horizontally and not in the y direction. What I'm writing here is just going to be for the y direction. And then the acceleration is little g. The displacement delta y is going to be a negative 0.52 meters down, and I'd like to know the time. One thing that's not involved here is the final velocity, so I'm going to pick an equation that doesn't have final velocity in it. So how about going over to my equation sheet and I say delta y equals VOT plus 1/2 AT squared. As I mentioned before, some people like to put a little y down there to remind them that this is not about the x direction at all. So the y velocity is going to be 0. Initial y velocity is going to be 0 because it was shot perfectly horizontally. And so the y displacement is going to be negative 0.52, not 15. They put that there to try to trick you. We're not going to be tricked. Half of negative 9.8 meters a second squared, and the time squared. So I'll take and divide the 0.52 meters by half and by negative 9.8 meters a second squared to get the time squared. When I do that, I end up getting 0.326 seconds. And then when I take the square root of that, I end up, before I take the square root of it, I have 106 seconds squared. And then once I take the square root, at 0.326 seconds. And so that's how long it takes for the arrow to reach the target. Number 41 and 42 are about a soccer ball that's kicked from the ground with an angle. Now, this is going to be something that's a little bit different and a little bit harder than what we've done in class so far. If you take something and you kick it in an angle like that, now it doesn't have a 0 y velocity initially. It has something. Here's what I mean. If I took that ball and I kicked it at an angle of 32 degrees, so the initial velocity looked like that, well, there's an x component on that, a VOX, and there's a y component on that, VOY. See how that's different than something that's just launched totally horizontally and it's not up or down at all. Now, they tell me that this angle right here is the 32 degrees, and they tell me that the initial speed is the 12 meters per second. So if I want the initial velocity in the x direction, I'm going to take that 12 meters per second, and since that VOX is right beside the angle, I'm going to multiply by cosine of 32 degrees. If I do that, I end up getting 10.177 meters a second. And if I want the VOY, since that VOY is not touching the angle, and if you want to see the triangle, I could move it over here like this. Since it's not touching that, I can make it 12 meters per second sine of 32 degrees. And so that's going to end up giving you 6.359 meters per second. Hey, I wrote a lot of significant digits, but both of those are only 2 significant figures. All right, so now I'm going to proceed the way I did before. In 41, they say, what are the x and y positions of the ball? So in the x direction, in both directions, I'm going to use the delta x equals VOT plus 1/2 AT squared. In the x direction, I'll make that VOT, so 10.177 meters a second times the time of 0.507. They gave me that in the problem. And the second term is going to be 0 because the acceleration is 0 So I could put a 0.5 in for t, but that's whole thing's going to 0 anyhow. And so I could say that that is 5.0885 meters, and only two significant figures on both of those. So we'll make that 5.1 meters. In the y direction, similar thing, VOT plus 1/2 AT squared. Now this time, for the last few examples that we've done, VO has been 0 in the y direction, but this time it's going to be 6.359 meters per second times the time of 0.5 seconds. Now, be careful here. The initial velocity was up, so I made it positive, and this acceleration is down, so I'm going to make it negative, and 0.50 seconds squared there, and that's going to give me a delta y of 1.9545. I'll round that to 2.0 meters. Now on number 42, they ask about the x and y component of the velocity 0.5 seconds after it was keyed. So the x is very, very easy because as we talked about in class, the x velocity is going to be a nice constant. A nice picture for you to think of is here's that along the parabolic path that the travels on, here's the ball at a few locations along there. And the x velocities are always going to be the same size. Always the same size. How come? We say inertia. We don't really know why that's the case, but we know that things will maintain their velocity if there's nothing pushing on them. So we're going to say that the v final x is the same as the v initial x. If you want an equation for that, it's Vf equals v naught plus at. That's right off your formula sheet. But since the a is 0 in the x direction, the final is equal to the initial, and so it started off at that 10.177. So it stays at that 10.177. Now in the y direction, it's a little bit more of a calculation. So in the y direction, I'm going to say that the final velocity in the y is the initial velocity in the y plus the acceleration in the y times the time. None of those are 0. The initial velocity in the y was the 6.359 meters a second plus a negative 9.8 meters a second squared, and the time is 0.5 seconds. And if you run all that through, you can see that this is going to be negative 4.9. So it's still going to be on its way up, but it's slower because it's been pulled down for a little while. 1.459 seconds will make that 1.5, not seconds, meters a second, of course. So it's not all the way to the top. It's going to be maybe in here somewhere. If I wanted to show you those y velocities on this, I'd show something like that, and then a little less, and then a little less, and at the very top it has none because it's not going up or down for just that instant. Now when it's on its way down, it's like this and like this. On 45, it talks about Jennifer's bowling ball being dropped from rest. Here it is. And Janet's bowling ball being thrown horizontally. After the balls are released, is the acceleration of Jennifer's bowling ball greater than, less than, or equal to the acceleration of Janet's? Well, it's going to be the same. So if you took the paths, Jennifer's bowling ball is going to go straight down this, whereas Janet's is going to go in this parabolic path like that. Now, if you took the ball at any moment and you did the free body diagram for it, remember this is the forces, the only thing you'd see on either one of the balls is gravity acting down. And because gravity is the only force acting on it, that means the acceleration is going to be the same. And that's why they end up hitting at the same time. So acceleration is going to be equal for both of the balls. 46 is a neat one. There are 3 projectiles, A, B, and C, launched with the initial speeds but with different angles. Rank the projectiles in order of increasing horizontal component of initial velocity. So you see all of these are the same size. Maybe A is like that, B is like that, and C is like that. I tried to draw all those arrows the same size. Do you see something? A's x component is not very big. B's x component is bigger. I'm drawing to right underneath the tip of the arrow, and C's is the biggest of all. So it's all the way to there. So if I were to rank them in terms of horizontal component of initial velocity, I'd rank them increasing, so I'd say it was ABC. Now for part B, we're supposed to rank them in terms of time of flight in an increasing way, and there's a couple ways to think of it. One way that I like to think of it is I like to think about the vertical components. So now C has the smallest vertical component of its initial velocity. B's is bigger, and A's is the biggest. You can see the effect of that. Look how high up A goes versus B. C doesn't go up very high at all. Well, you keep going up until gravity can bring you to a stop. So it's going to take gravity the longest amount of time to stop and bring back down something that started off very fast up. So A is going to be in the air for the longest, and C is not going to be in the air for very long at all because every second gravity will change your velocity by 9.8. And so it's going to take gravity not long at all to stop and bring back down C, and the longest for A. So those are going to be the opposite, C and B and A. 81's a real thinker. On 81, all of these projectiles get up to the same height, and they want you to rank them in increasing initial speed and of time of flight. Well, if you're paying attention on the last one, I said that on the last one, they had different initial velocities, and that's why they got y velocities, and so that's why they got to different heights. Now here they all get to the same height, so that tells me that they all had the same initial y velocity. So A has a y velocity, it's big, so does B, so does C. Now here's the thing, C goes a lot farther, so that must mean that it has the biggest x velocity, and B must be in the middle since it doesn't go as far, because they're all going to be in the air for the same amount of time. Why? Because they all went up to the same height. So time of flight, they're all the same. So if they're in the air for the same amount of time, then they must be going faster. C must be going fastest. That's how it gets farthest. So in terms of initial speed, take a look. Initial speed for C is real big like that. And you might be saying, well, isn't that the velocity? But just the magnitude of it is the speed. The initial speed of A was like this. I bet you saw coming that B's was in between. So if we're going to take the increasing, the red arrow is the shortest, so we'll make that A, then B, and C. All right, everybody, in number 49, we talk about a softball thrown from the origin, which means that the initial x and the initial y is going to be 0. And we say it's thrown from the origin with an initial speed of 18 meters per second and an angle of 35 degrees above the horizontal. So horizontal, of course, like this, 35 degrees above the horizontal will be something like that, initial velocity of 18 meters per second, and 35 degrees above the horizontal. Now, you see later, they want you to figure out the x and y positions of the softball. And so I will be using the equation, we put it up here, delta x, or displacement, will be equal to initial velocity times time plus a half of the acceleration times time squared. So I like to say I'm going to need the initial velocity for each direction when I do the x and y. So the initial velocity in the x direction looks something like that, at VOX, and the initial velocity in the y direction looks something like this, VOY. Now, if you're starting to catch on to components, you might be able to say, I realize the VOX is 18 meters a second cosine of 35 degrees. Now, if you didn't know where that came from, I want you to stop the video and I want you to write out, take the triangle and make it actually look like a right triangle like this. And then I want you to label what's opposite, adjacent, and hypotenuse, and then think of which side is the adjacent, and then you're going to use for that. You'll see that that process gets you this blue side. It'll be a similar thing for the black side. Now for the blue one, you go ahead and put in 18 cosine of 35 into your machine. You're going to end up getting 14.744 meters a second. Only two of those are significant. And similar to that, for VOY, we're looking at 18 meters a second sine of 35 degrees. And if you do that, you end up with 10.324 meters a second, two significant figures. Okay, now they want you to just find the X and Y positions at those 4 times. And so what you're looking at in the X direction, you're going to say that delta X, which remember delta X is the same as final minus initial X. The initial X is 0, so really this is for figuring out the final velocity after half, 1, blah, 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 seconds. That's equal to the initial velocity times time plus a half of the acceleration times squared. Now, remember, this is just for the X direction. So there is no acceleration in the X direction on a projectile, so this term is going to go to 0. So this X final is going to be nothing more than the initial X velocity, 14.744 meters a second, times whatever you're going to put in for the time. And you're going to go 0.5 once, you're going to go 1.0 once, you're going to go 1.5, and you're going to go 2. Whenever you do that, you're going to get 4 different answers. Now, you peeked at the end, so you know that eventually they want me to graph this. So I'm just going to write this data in the T-chart, time in seconds and X in meters. And so 0.5, 1.0, 1.5, 2.0, and that's going to give me 7.372 meters, 14.744 meters, 2.166 meters, and 29.488 meters. And where did I get those? Well, I just multiplied 14.7 by 5 by 1 by 1.5 and so forth. Now I'm going to do a similar thing in the Y direction, except in the Y direction there's a little more there because there is acceleration. In the Y direction, my initial velocity in the Y times my time plus half of my acceleration in the Y direction times time squared. Well, this is, remember, delta Y is, just like I said before, final minus initial Y. That initial Y is 0. They said it was thrown from the origin. So the final Y is going to be the initial Y velocity, which is 10.324 meters a second times the time plus half of the negative 9.8 meters a second squared times the time squared. And so just like before, you're going to substitute in 0.5 and 1 and 1.5 and 2, but this time you're going to substitute it into 2 places. You're going to put it right there. You're going to put it right there. So whenever you run that through, you end up getting time and Y of 0.51, 1.5, and 2. And those Y values end up coming out to 3.937, 5.424, 4.461, and 1.048. All that's a little bit more significant figure than you'd actually need. So there are the X and Y positions of the softball at those times. Now what they wanted you to do to finish this off in part B, they wanted you to take and plot a graph of X versus Y. So essentially, where is it in space? So I want to graph the point 7.372, 3.9. So down here on this x-axis, I went every 2. So 7 would be like 7.3 would be like in that ballpark, and 3.9 would be almost all the way up to that 4 mark. And so we're looking like something like right here for the first one. Then I'm going to graph 14.7, so 10, 12, 14, almost in the middle of that, and then up to 5.4. So I've come over here, 10, 14, almost 15, 5.4 is like this, and then 22.1 and 4.4. So I'm going to come up here, something like that. And then last 29, 30, and 1, just a touch more than 1. That's probably a little bit too much. And so there you go. And so now if I wanted to sketch a nice smooth, try that one more time. Nice smooth parabola through this. Pretty good. Like this. One thing that I do notice whenever I see this is I see that the y-intercept is not 0, which does make sense. They called the place where the ball was thrown the origin, and that is going to be a little bit higher than the ground, and so that makes some sense that when you throw a softball, you don't throw it off the ground, you throw it to the air a little. That's about the right height for a person to